Yeah, I'll start the recording here first. So yeah, these are the few things that we will not have time to go through. Okay, superposition, the principle of superposition, standing waves, then thermal physics of zeroth law, first law, and black body radiation. Okay, basically it's just a formula for first law, just a formula which I already put it in a formula sheet. So let me check. Yeah, correct. So yeah, just go and read up on what it is. It's not that hard. Okay, it's just a matter of conservation of energy. Then the last thing, okay, that you need to read from a textbook is this thing called electromagnetism and electromagnetic induction. Okay, so these are the third last and second last chapters on your textbook. Now, your textbook also have nuclear physics, so that part, while it's in your O-level syllabus, is not in the Olympiad. You can skip that part first. Okay, so electromagnetism, electromagnetic induction, where you need to know your Fleming's left-hand rule and Fleming's right-hand rule. And you don't need to know the explanation. Okay, you just need to know the laws and the rules, roughly know how it works. And for O levels, basically, these two chapters are heavily explanations. Okay, so you learn how to determine direction of forces and direction of induced current, etc. But in terms of the formulas you need, okay, I also put it at the bottom right side. Okay, so some of the formulas are there. You can go and take a look. Yeah, so again, if you need, you can always download JC Notes. I believe you all know where to download. Okay, just search for it. Okay, so you can just download some of the school's JC Notes and just look through these few chapters. Okay, there's only like 1, 2, 3, 4 chapters here. So these are the things that we will not have time to go through. Okay, especially the last one because your school hasn't even teach yet. Okay, that one is usually around July. Yeah. This one? Oh, oh that's fast. Okay, which is good. Oh, okay. And then your school teach this already. Then at least you all finish this and finish this. Good enough for Olympiad. Okay. I don't think they will come out very heavy on this, so it should be up to the lesson 6, which should be the heaviest. Yeah, so I choose, and then after that, I think thermal will be heavier. These two should be lighter. Although it's in the syllabus, it's lighter. Then there will be one more thing, right, which I realize I miss out, so I will go and type it out and probably send to your teacher to send you all a soft copy to read, which is this thing called coefficient of restitution. Yeah, I was like checking through the syllabus again. I realized I missed this thing. Coefficient of restitution. Okay. Yeah. So this one you might want to also Google for it, but it's actually a very simple thing. Okay, it's like when the ball is bouncing, okay, you know that the height reduces as it bounces. Why? Because there's energy loss. So the energy loss, the percentage of it is all part of coefficient of restitution. And it can be used together with conservation of momentum. Okay. Okay, so those are the few things that you're left with after we finish the next week's lesson. Okay, so these are the remaining things you want to look through before your Olympiad. Okay, so today we'll go through this thing called gravitation. Okay, now this is also a JC chapter, but what I'm going through today is very restricted and specifically catered for Olympiad only. Okay, some of the things up to lesson 3 is still very JC. You can reuse them, look through them again. With, like let's say December, you want to look through to prepare for your JC, can. But this part, only the formulas are there, but the applications, only some is in, some not in. Okay, so I have 5 applications for for Olympiad, but for JC I have like 23 applications. Yeah, something like that. So I can't go through everything, of course. Okay, so we'll go through gravitation today. Then after that, electric field, and last part, capacitance. Okay, capacitance is in your new JC syllabus. Okay, so on gravitation now, for at O levels, this is what you have learned. Okay, you learn that gravitational forces are downwards. Okay, and we know that it's constant at 9.8 meters per second square. That's your gravitational acceleration. So because of that, when you draw gravitational field lines, I hope you all remember your field lines. You all have done gravitational field and electric field at O levels, at least a little bit. So field lines for gravitation is downwards because the forces are all downwards. And because the field strength near the surface of Earth is constant, they are also evenly spaced. Okay, so if you recall from your own O levels, right, you have gravitational field, you have electric field, you have magnetic field. So as long as it's a field, as long as the field strength for any of these field are constant, they will be evenly spaced. Okay, remember that how far the field lines, right, how far apart they are, will tell you the strength of the field. Okay, so that is the reason why, let's say, for let's say a positive charge, okay, you all usually draw, if you can recall this, what you draw for O levels. Okay, why do you draw like this? It's because you can see that yes, it's in all directions, but as we go further and further, the distance between the lines is larger and larger, which shows that the electric fields gets weaker and weaker. Okay. Now, for gravitational field, right, the direction of the field lines tells you the direction of force on a mass. Okay, so yeah, that's why it is all downwards. Okay, as long as you have a mass, it tells you that okay, the gravitational force is going to be downwards. Okay, so up to here is still O levels. Now, what does downward really mean? When we see on the grander scale, this is what happens. Okay, at every point on Earth where you are standing, the field is downwards, which means perpendicular to the surface of Earth. And we already know that Earth is a spherical mass, unless you want to believe in flat Earth theory. Okay, yeah, so it's a spherical mass. So at every point on Earth, okay, you think of it in 3D, downwards means the force, the gravitational field, is going to be perpendicular to the surface. And we can say that, in a way, if you extend all these field lines, they will all intersect at the center of Earth. So, in general, we say that the field lines, the force, okay, is always not just directed downwards, that is because when you're near the surface of Earth, but it's directed towards the center of Earth. That is your gravitational force and gravitational field. They will all converge at the center. But inside, of course, we don't do anything to it. Okay? Up to here, okay, right? Okay, so next, so which brings us to this. Newton's law of gravitation. Okay? So every particle in the universe, it attracts every other particle with a force that is directly proportional to the product of their masses. Okay, make sure everything. And inversely proportional to the square of the distance between them. Okay, so what this means is that the gravitational force is proportional to the product, okay, m1, m2 of two masses, and inversely proportional to the distance between them. And the constant of proportionality is given by this thing called the gravitational constant, G. Okay, huh? Don't know how they determine. This one is based on a lot of measurements last time. If y'all go and read through the story of Kepler third law, right, you will realize how genius and how he and Newton were. Okay, but anyway, the constant of proportionality is called the gravitational constant, and this is what we call a universal constant. Okay, a universal constant is something that is constant throughout the universe. Okay, now there is a negative sign here which I was thinking whether to put in or not to put in, but I just left it in. So we do not need to use it in your calculations. It just signifies that gravitational forces are always attractive. Okay, because forces are vectors. So in a way, right, this is a vector. You all learn vectors match already, right? So it's like I put a unit vector R here. So the force and the distance, the displacement are actually opposite in direction, which tells you that which is like this, okay? So it tells you that it is an attractive force. So this law of gravitation, right, is telling you that as long as there are masses, okay, there's a mass there, it will exert a gravitational force. Why that happens, nobody knows. Okay, we are studying in a lot of things in physics, nobody knows what is happening. So we are only studying the effects of like in this case, the effects of gravitation, the effects of what mass is doing. Okay, so you can see that from I don't know which level you learn what is mass, okay, which is a measure of inertia. Before that, I think mass, I don't know what is mass. Yeah, maybe what is matter, which is something that has mass and occupies space. Okay, then after that, you learn mass is a measure of inertia. Now you see that mass can also exert a gravitational force. Okay, you can see it builds up. So now the first question you can think of is, if mass exerts an attractive gravitational force, right? Why is it that, let's say, the water bottles on your table, why do they not attract each other and like come to each other? Okay, and the reason is that, yeah, the mass is too small. So yes, there is still gravitational forces between them, but it's too small and it cannot overcome the friction. Okay, so in fact, they have actually proven, I don't know how they do it, I cannot remember the exact experiment, you can go Google for it. They used very sensitive equipment to use small masses and prove that even for small masses, there's still gravitational force between them. Okay, so the one you can just Google for what they did. Okay, so yeah, so that proves the law of gravitation. Okay, for that particular experiment. Okay, so now that you know this formula here, okay, you can see that is the reason why Earth exerts a strong gravitational force on you. Okay, because why? What is the mass of Earth? Okay, I'll give you here. Mass of Earth is where can I write? Maybe I write it here. The mass of Earth, right? Okay, G first. We talk about gravitational constant. Gravitational constant is a very small value, 6.67 times 10 power minus 11. And that is the reason why, let's say again, the gravitational force between two water bottles is so small. It's in the order of 10 power minus 11. Okay, but the mass of Earth is around 5.98 times 10 to the power of 24 kg. Okay, you think of that versus the mass of Moon. The mass of the Moon, right, is around 7.2 times 10 power 22 kg. Okay, you can see all these masses are like way larger than the mass of human. Okay, not just that. How about, what is the diameter of Earth? This is in your syllabus. You're supposed to know the size of the atom to the size, the diameter of Earth, which came out 2 times in your TYS. Oh. Okay. Oh. I give you all the radius of, okay, for O levels first. Okay, for your the size of, let's say, atom first. Atom is 10 power minus 10 meters. Okay. Earth, the diameter is 10 power 7 meters. And what came out for your also before was, what is the diameter of the strand of hair? These were the 3 things that came out for TYS in your TYS. Okay. Okay. Now the actual radius of Earth is around 6370 km. Okay. Now depending on the question, sometimes it may be 6380, sometimes it may be 6370. Okay, so you see the question, what the question gives you. Now, because the radius of Earth is so big, now let's go back to understand what is called near surface of Earth. How far is near surface of Earth? Okay, so this is Earth radius, 6370 km. Now the highest point on Earth, you know, is Mount Everest. Okay, what is the height of Mount Everest? It is about, Everest is 8848 meters. Okay, and the deepest part is the Mariana Trench, okay, which the segment called Challenger Deep is around 10 kilometers. This one is around 8.8 km. And you can see that in both cases, right, it's negligible compared to this. Okay, in fact, even on a plane, let's say you're flying on an aircraft, you don't feel your weight dropping significantly. Okay, that's probably, I don't know how many, yeah, that one is, I can't remember what is the, like, okay, aircraft investigation always have around 28,000 meters. Even that height, okay, is still like less than 1% of the radius of Earth. So in that sense, right, it's still negligible. So that is still near we consider as near surface of Earth. Your gravitational field strength is still uniform. Okay, what is called far away from Earth? one of the probably one of the uh nearest that you can think of is the International Space Station. Okay, which again is also in your TYS. Yeah, all these are new. I'm using information from your TYS. If you all have done it, you probably will know it. Yeah, so one of the questions in the TYS actually state that the gravitational field strength at the International Space Station is 5 newtons per kg, not 10 newtons per kg. Okay, then the question comes within your own TYS. You can go and check. Why is it that even though the G is 5 newtons per kg, the astronauts are floating within the space station? Okay, we'll come to that later part. I have. Okay, it's all within your. It's your what your it's in your Tangle series. Just go and do. Okay. Now we come to the next term, gravitational field. Okay, so field strength. Okay, I think some parts I need to make sure the definition is there. So behind I might have some wrong definition. Later I need to ask you all to add in some words. Okay, field, right? Okay, is a region of space. In this case, gravitational field. Okay, it's a region of space where a mass experiences a force. Okay, force. The English fail. Experiences a gravitational force of attraction. Okay, don't know what happened here. Okay, anyway, just gravitational force. Okay, some English error here. So in physics, okay, which is also in our new syllabus, there's the understanding of fields is important. Okay, fields, we don't normally talk about field of force. So fields represents a region of space, okay, where there's a non-contact force. So in physics, there are only three fields: gravitation, electric, magnetic. Right, only these three. So here we are learning gravitational field. Later part we'll learn electric field. Magnetic field you just learn from your own textbook. Okay, nothing very special. So the other thing is this thing called field strength, which is defined as the force per unit mass. Okay, so when you see the thing like let's say on surface of Earth, 10 Newton per kg, this is called gravitational field strength. Okay, it's the force per unit mass. If you see 10 meters per second square, this is called gravitational acceleration. Okay, while you use in terms of calculations, they are interchangeable, but the understanding, the meaning is different. Okay, one is on field strength, force per unit mass, one is gravitational acceleration, okay, which is the rate of change of velocity. So now you learn two terms, force, field. Okay, later we'll come to the equation. The next two terms, gravitational potential energy and gravitational potential. Now, you don't need to know the definition here. Okay, this is the definition for JC. I didn't fix it based on the JC one because there's an update. Okay, so I update for your new syllabus. Just that I will just warn you first. For JC, there are two JCs who don't want to follow the syllabus and add extra words for the definition. Okay, so if when you go JC and you take physics again, must make sure your definition follow your school notes. Okay, some of them are very strict. Okay, so come to here now. Gravitational potential energy. What is the formula you learn at O levels? MGH, right? Now MGH has two conditions. Okay, number one, it must be near Earth. Yeah, even you're on the plane still near Earth. I think it'll be quite obvious. Huh? That one not near. Okay. Number two is equals to 0. GP is equals to 0 when H equals to 0. So there is a point where you define as H equals to 0. Of course, if the H equals to 0 is above, your GP will be negative. It can be negative. Okay, because it's with reference. If the H equals to 0 is at the bottom, of course your GP will be positive. Okay. So near Earth, okay, to be more proper, where G is constant. Now, it may not be you for Earth. Okay, you can use it for near moon surface, near Mars, the surface of Mars also. Okay, any planet also the same thing. Now, when we go further away, okay, now this is the formula. Negative GMM over R. Negative, the negative is important here. Huh? So this is the gravitational potential energy, okay, of a small mass m to and a position within the gravitational field of a large mass m. Big M here, small m, okay? And in this case, we are taking GP equals to 0 at infinity. So it's with reference to infinity. Okay, there's a reference point. Now, the reference point is defined to be infinity. Infinity is subjective. Yeah. Yeah. For ends, the other side of the classroom is infinity. Yeah. So it's quite subjective. Okay. So let's say you have Earth. We use Earth as an example here. Let's say you're at infinity. Your GP is going to be 0. Okay. GPE 0. So as we go towards Earth, do we gain or lose GPE? Lose, right? It's like you drop nearer to Earth, nearer to the ground. So because you lose GPE, you are losing from 0. Your GPE is always negative. Okay. This is, I'm using a simple way. This is not the A-level explanation way. Okay, I'm using very simple so that you all understand. So at infinity is 0. Later I'll explain the A-level way in a while, but yeah, for now you try to understand first. At infinity is 0, and as we move nearer to Earth, you know that there's a loss in GP. So 0, and you lose GP, you get negative GP. So GP is always negative. Okay, now let me explain using force time distance. Yeah, but it's still from Earth, like consider. Okay, later we do the questions, you understand. Okay, so now the GP is now defined as the work done by external force to bring a mass from infinity to the point. Okay, so for a mass here, we talk about work done by the field first. From infinity to here, this is the displacement. This is the force. So in this case, this force is exerted by Earth. We say that the work done by the field due to the Earth is positive. An external force will actually exert a force in the opposite direction to the field. So work done by the external force is negative. Okay. Now, if you don't understand it, my dear, just leave it. Okay. Just know that it is always negative in value. Okay. And the last term you need to know, all these are terminologies only, is gravitational potential. So difference between gravitational potential and gravitational potential energy is this extra per unit mass. Usually you want to look at this because let's say you look at a planet, okay, or look at a star. We are just looking at its own field, okay, how it will affect other masses. So you look at its field, you look at its gravitational potential. Okay. Okay. So we come straight to here. A quick summary of the equations you need to know. Okay. So there are only 4 terms. Law of gravitation only gives you this. Okay. Again, the negative sign you can ignore. This is the force. This is the field. Field strength, to be more proper, I forgot to add in the word strength. So this field strength is force per unit mass. Add in the word strength here. Okay. This is potential energy. This is potential. So you can see that above here, right? These are, okay, the whole thing. These are vectors. At the bottom, everything here, okay? So everything that is here, these are scalars. So vectors, because they have directions, okay? The negative side, when you do your calculations, you can just ignore because we just know that it's an attractive force. Okay, but for scalars, you cannot ignore the negative sign because we are taking with reference to infinity. Okay, now let's do some simple questions. Go a few pages later, the basics. Okay, look at this first thing, which also an application in a way. Okay, so this first thing is called neutral point. Now, a neutral point is a point where the between two masses, where the net gravitational field strength is 0. Okay, net gravitational field strength is 0. There are only two places where field strength can be 0. One is at infinity, one is at the neutral point. Okay, so at the neutral point here, okay, it will always be nearest. I'll just tell you straight, it will always be nearest to the smaller mass. Okay, later I'll explain in maths why this is so. But it will always be nearer to the smaller mass. So we'll let this point be the neutral point. Okay, you can see that for gravitation, right, you'll always be in between. Why? Because at this particular point, there will be gravitational field strength due to the 30 kg to the right. There will be gravitational field strength due to 50 kg to the left. Because gravitation is attractive. Okay? Which tells you, okay, that because they're opposite direction, at this point the net field is 0. So these two, right, must be equal in magnitude, opposite in direction, such that they cancel each other out. Okay? Now gravitational force, the formula for field and force, the R, right, is always the distance from the center. So center to center. And we'll let this distance from the 50 kg to the neutral point, let this be R. Okay, which tells you that here must be 10 power minus 3 minus R. Okay. So because this at the neutral point, your gravitational field strength is equals in magnitude opposite in direction. Okay, the net is 0. We have G M, okay, G M over R square equals to G M over 10 power minus 3 minus R square. Okay. G is a gravitational constant. But in this case, they will cancel each other out. Just cancel the 10 also, reduce to lowest terms. From here, you get 5 10 power minus 3 minus R square equals to 3R square. Okay? Don't expand, no need to expand. Just square root both sides. We will reject this because this is positive and this is positive. So from here, you can get your r of root 3 plus root 5 equals to root 5 times 10 power minus 3. Okay, I think it's this value. 0.563. Okay, so which is going to be 0.564 mm. So that is the location of the neutral point. Okay. Next, conservation of energy. Okay. So here we use the field formula. Here we are going to use conservation of energy formula. Okay. So a satellite is moving towards Earth at 700 meters per second, 2 times 10 power 5 meters away from the surface of Earth. So you can see sometimes they like to use this term, from surface of Earth. Okay. So when they give this value here, you must always remember to add the radius of Earth. Because again, your gravitational law of gravitation is always from the center of Earth. Distance from center of Earth. Okay. So given that it eventually crashes on Earth's surface, what is the speed? Now it's the same type of question, the similar type of question for something that you drop and hits the Earth's surface. Okay. So for those questions, when you apply conservation of energy, you know that there is a loss in GPE equals gain in KE. Loss in GPE equals gain in KE. Now, loss in GPE is not MGH here. Okay? Because we are no longer using MGH. It's far enough. So, any losses is always the initial value minus the final value. Okay? Or you could also decide, if you like, initial GPE plus initial KE equals final GPE plus final KE. This or this also can. Okay, just that for loss, it's always, or take it as it's always the initial minus the final. And for gain, is the final minus the initial. I hope you all can see that these two formulas are the same. If I move this initial to the other side, let's move this to this side, you'll actually get this. And if you move this to the other side, you'll get this. Okay, so loss, initial minus final. Now, the initial is at a distance of 2 times 10 power 5 away from the surface of Earth. So the initial GP is negative G mass of Earth, mass of satellite over R, which is 2 times 10 power 5 plus 6370000. Initial GPE minus final GP. By the way, this particular question, because I scared some of you may not have time to copy, is already at the back. Okay, your final page, I think, have the same question with your word solutions. Yeah, right here. Okay, the top one. So this is equals to gain. Final minus initial. So half mv square, the final speed, minus the initial speed. This is mass of satellite here. So just cancel the mass of satellite, sub in the values. You should get a very nice value. Okay, can? Okay, we go back to the notes. Okay, some quick applications here. Okay, so the law of gravitation, right? Okay, apart from forces, it's still a it is still a formula for force. Okay, so one of the types of question which I did put in, you can have that theoretically mass 1, mass 2, and mass 3. Find the resultant force on, let's say, mass 3. Find the resultant force. So you just need to find one force between here. Let's call it F13, and one force here. Okay, F23. Find the angle between them if they give you, and just resolve vertical, horizontal, find resultant force. Okay, so that type of question I'm not going through here. Okay, it is a potential question which came up for electric field. Yeah, later you'll see electric field is just a step up from here. Okay, so it's a very yeah, it's not much more difficult than this. It's about the same. Yeah, so that is for application of it as forces. Now, because gravitational force is still a force, okay, we can use it to analyze orbits. Now, most orbits, at least within the inner solar system, is circular. Okay, so let's say for the moon around the Earth, most satellites around Earth, Earth around the sun, all these orbits are assumed to be circular. Of course, if you look at those in the outer solar system like Pluto, okay, Uranus, Neptune, the orbits are actually elliptical. Okay, I'll talk about that in a while. So let's say for circular orbits, remember for circular motion, for things to move in a circular motion, you require a centripetal force, which is the resultant force on the object. So for orbits, what happens is that, let's say for the moon around Earth, the gravitational force of Earth on moon provides the centripetal force for the moon to orbit around the Earth. Okay, the moon also exerts a force back on Earth. This is Newton's third law. Okay, now because the Earth exerts this gravitational force, which provides a centripetal force, we can say that gmm over r squared, this is the gravitational force, equals to mv squared over r, or mr omega squared. Okay, so you can use either one to solve questions. Now, if we actually expand on this, omega we know is 2 pi over t. So this part here is actually r cubed times 4 pi square over t square. You can rearrange 4 pi square over t square. We could actually rearrange to get t square equals to 4 pi square over gm r cubed. And this tells you t square proportional to r cubed. Okay, no, just small r. So for orbits, t square proportional to r cubed. This is Kepler's third law. Now Kepler is somebody before Newton. So what happened was that before Kepler, there was one person who actually took all the readings of the period of the orbits of the planets and the distance from the sun. So I don't know how he do it, but they managed to do it. Okay. And he took all these readings like that look like random numbers. Then Kepler studied all these numbers. Okay, the person I think is before Kepler. He passed the things to Kepler because he passed all the readings to Kepler to continue the work. Okay, so they actually spent a lifetime trying to decipher the readings, which they didn't manage to do. And by the time Kepler, based on all these random readings, somehow he came out with T square proportions of R cube. If you can look at you can go Google and look at the data that he had. Okay, just some random numbers. And you must remember that was a time with no calculator. So he managed to come up with T square proportion of R cube based on empirical readings. Okay, and Newton came years later with the law of gravitation and proved it. Yeah, so this is for circular orbits. So it also tells you that the further the distance from the sun, the longer the period. Okay, so Mercury will have a shorter period, and Mars will have a longer period. The year is longer, maybe like 365 days, for example. Okay, so up to year, okay, not that hard. These orbits are circular. Now, the thing about the solar system is pretty interesting. That if you have the sun here, right, the inner solar system are still all almost perfectly circular around the sun. But those at the outer solar system, okay, some of the orbits are actually like, okay, this is probably exaggerated, but yeah, it's actually going to be, it's actually elliptical. Okay, so this first happened for Uranus, which was elliptical. So because of that, they suspect that, okay, there must be probably another planet that may have affected Uranus orbit. And based on calculation, there's this mathematician who used the law of gravitation to calculate. And then he calculated where there should be another planet. Then he asked his astronomer friend to actually look. I forgot their names, but because of that, they discovered Neptune. Okay, so Neptune was the first planet that was discovered based on calculations. After that came Pluto. So Pluto's orbit is also elliptical, but for that, okay, at the moment, cannot be explained. Okay, nobody knows why. So that's why they suspect. Okay, you know that Pluto is now a dwarf planet. It's not a planet. It's not considered a planet anymore. So they suspect that because of that, there might be another planet out there that is not seen yet, not discovered yet, because of the law of gravitation. Okay, so there's probably a hidden planet. I don't know where that might attract it, such that it causes its orbit to be elliptical instead of circular. Now, the law of gravitation is also the reason why the solar system, right, when you see the pictures, right, is almost flat. Okay, space is still considered as 3D, but your solar system is almost flat because it's not just the gravitational force between the sun and the planets, but also between the planets. So if it's like 3D all over the place, right, then there'll be gravitational forces that will be probably harder to calculate. Probably like if like one is here, then you have two forces, a bit hard to calculate. Okay, so after billions of years, it settled down into a flat plane. Something like that. Okay, so that explains the solar system. Okay, now we go on to understand this next part. Yeah. Okay, to expand on that, what happens is that the circular orbits doesn't just happen for the planets around the sun. The sun itself, or the entire solar system, is actually moving or orbiting around the center of the Milky Way galaxy, okay, which is a black hole called Sagittarius A star. All the stars are assumed to be moving in a circular motion around the center. Okay, of course, black holes cannot be seen, okay, because that's why it's called a black hole. No light escapes. So it cannot be seen, but what happens is that people can observe the effects of it. Yeah, so yeah, okay. Okay, just to go on to that is like probably another 2-3 hours just on black holes. Okay. You can also Google for life cycle of a star if you're interested, but not in Olympiad. Okay, so the next part, okay, this one I don't know if they will come out if we expand on the circular orbit part. Okay, because for gravitation, I feel that one of the most important thing is orbits. So instead of just a small mass versus a large mass, okay, now there's another type of orbit that is between two objects of comparable mass. Okay, specifically in the universe, right? Most of the time, it's called the most common is a binary star system. So binary star system is a system of two stars. Okay, their masses are probably close to each other, and they orbit about their common center of mass. Now, center of mass, we talked about it a little bit during the last lesson on mechanics of rigid bodies. Okay, so again, we use center of mass for the universe because there's no uniform gravitational field here, so we are not going to talk about center of gravity. No, center of mass, okay, is similar to center of gravity if there's a uniform gravitational field. It is similar idea to center of gravity. So center of gravity is the point where all the weight seems to act from. Center of mass is the point where all the mass seems to be at. Okay, so let's say on the surface of Earth, our gravitational field is uniform. The center of mass and the center of gravity will be exactly the same point. But in the universe, right, we don't talk about gravitational field here already. It's no longer uniform. It's very complicated. So we use center of mass. Okay, so let's say for this case, there's a heavier mass. It's a lighter mass. You can see that the center of mass is actually nearer to the heavier mass. If we were to do a calculation, let's say this is M1, this is M2, this is radius R1, this is radius R2. It's as though we can do principle of moments. M1 times R1 equals to M2 times R2. Similar to principle of moments, but it is not principle of moments. Okay? And because of that, you can see that this center of mass, based on this formula, it must be nearer to the heavier mass. So you can see that it's different from neutral point. Neutral point is nearer to the lighter mass. And the reason is because you want the lighter mass to exert a greater effect, okay, to balance out so that they cancel each other. But for center of mass, okay, it will be nearer to the heavier mass because it's the point where all the mass seems to act from. Now, this binary star system is an interesting system, such that they orbit around each other. Okay, so when they orbit around each other, they orbit around this common center of mass, the center of mass between these two. The heavier one will have a smaller radius, the lighter one will have a larger radius. Their angular velocity is exactly the same. Okay, just imagine we have a rod in between. Okay, and what you are doing is just making here as like a pivot and just rotating these two around. Okay, so the thing is that it's hypothesized that most stars in the universe are in a binary star system. Okay, now, although that's the case, the sun is considered a lone star, means it's not part of a binary star system. Okay, just a standalone star. And the nearest star to us is also a lone star. It's called Proxima Centauri. Proxima Centauri. And the next two stars that are nearest to us is a set of binary star called Alpha Centauri A and B. So this is a set of binary stars that are nearest to the solar system. They are still like 4 light years away. Okay. Now, then you'll be thinking, why are they different? Now, they're actually not different. All the masses, when they're orbiting, is actually they follow this. Just that when you have a very large mass and a small mass, the center of mass is almost at the center. So you don't see it. Now you see, again, M1R1 is equals to M2R2. Then you think about Moon versus Earth. This is 7 times 10 power 22 kg. This is 6 times 10 power 24 kg. The difference is about 100 times. So if you have a distance between Earth and Moon, okay, you divide this by 100. Divide this red line by 100. The center of mass is still somewhere near the center of Earth. So you don't see it. Okay? But there's two orbits in our solar system that is near to this. Okay? The first one is Jupiter. Jupiter is the largest planet and has one of the heaviest mass. So Jupiter, right? Okay, let's talk about the Sun and Jupiter. Jupiter is heavy enough such that the center of mass of these two is at the surface of the Sun. So as the Sun orbits around this point, Jupiter also orbits around this point, not exactly at the center. About here, due to the gravitational force of Jupiter. Yeah, but Jupiter is large. Okay. The other system is Pluto and its moon Charon. I think it's pronounced Sharon. Like Sharon. Okay. I don't Charon or Charon. Maybe I should go and find out. Okay, so Pluto and its moon, the mass is quite similar, and they also orbit around their common center of mass, as they also orbit around the Sun. Yeah. Pluto has 5 moons. This is one of the bigger moons. Yeah. Okay, but it's not called binary star. Okay, it's just it's a system. Now for such systems, right, your calculations are slightly different. Instead of GMM over R squared, it's just GMM over the sum of the two radius, because the law of gravitation about the distance between them, but circular motion is about the radius of rotation. That's why there's this difference. No, it's still centripetal force, mr omega squared. This one is the centripetal force of M1, this is centripetal force on M2. Yeah, you can say 2. And you also have M1 R1 equals to M2 R2. 3 equations. Okay. By the way, something like this came out in 2016 A level. Okay, so these are okay. Okay, next one. Understanding high tide, low tides. Last year I wrote everything out. Then after that, this year I type out everything, so you all don't need to. So you can read it straight. Okay. High tide, low tides are also due to gravitation. And in this case, it's due to the gravitational force of Moon on Earth. Okay. So as Earth rotates, Moon pulls the water to the side. But Earth is rotating, so you'll bulge on both sides. So you get high tide, and here you get low tide. The Moon exerts a force. No, it's just because of Earth's rotation. Okay. Yeah, something like that. Very simple. Okay. Yeah. Just know that it's due to the moon's gravitational force. Okay, next one. Tidal locking. I put a link for y'all to go and find out. There's quite a few animations here. Quite interesting. Okay. So tidal locking, in short, okay, just use examples to explain. Moon is tidally locked to Earth. Okay, every time we look at the moon, we see the same side of the moon. It's not that it doesn't rotate. It rotates. Yeah. So why that happens? Okay, let's say again we have Earth. This is Moon. Okay. Now, as the moon moves around Earth, the moon also rotates about its own axis. Okay. So at this point, the moon is, let's say this is the part of moon that is facing Earth. Let's copy, paste. And at this point, this is where the moon is. The green side will face Earth. You can see that the moon moves in this direction, for this case, okay? At the same time, the moon also rotates about its own axis. So for the moon to be tidally locked to Earth, the angular velocity of the moon is equals about its axis. About its axis. I don't know if I wrote it somewhere inside. Yeah, never mind. It's equals to the angular velocity of moon about Earth. Because of that, we always see the same side of the moon. Okay? The other side of the moon, right, is what we call the dark side of the moon. If you go and look at all the things that they explore, okay, I think so far 2 countries managed to explore this part. It's called the dark side of the moon. Okay, it's a challenge to explore this part because radio waves are not able to pass through moon. So they will need a satellite at least to relay information to the rover here. Okay, they cannot control directly. So moon is tidally locked to Earth, but Earth is not tidally locked to moon. So on Earth, you always see the moon, the same side of the moon, but on moon, you always see different parts of Earth. Now, this tidal locking is interesting because, again, Pluto and its moon again, they are tidally locked to each other. Yeah. By the way, 2017 A level. Okay. I'm just taking all the stuff and just simplifying for you. How it happened, nobody know. Why is there a universe? Big Bang Theory. Nobody can prove. Okay, we are studying the effects of what has happened, what probably settled down into its own equilibrium billions of years ago. Yeah. So Pluto and its moon Charon again, they are tidally locked to each other. So their angular velocity is also equal to the about their own axis, right? It's also the angular velocity of their orbits. On a period of rotation about their axis is the same as the period of their orbits. So because they are tidally locked to each other, okay, you can just imagine that on Pluto you always see the same side of the moon, and on its moon you always see the same side of Pluto. There's like direct line of sight at all times. Okay, so that is called tidal locking. Okay, final application here, understanding the equatorial bulge. So basically, we know that Earth is not a perfect sphere. Why? Okay, Earth is slightly squashed at the poles, and the reason is because of there are 2 things that affects it. One is the rotation of the planet about its own axis, and one is the density of the things on the planet. Okay, the density in a way. Okay, so no, it's the less dense of for the same rotation in your bulge mode. Okay, so these are just. Hey, I asked AI help me compile this. Should be correct. I hope. I never checked the rotation period, but yeah, we know that Mercury is at least I know that Mercury is almost perfectly spherical. Reason being, Mercury's rotation about its own axis is very, very slow. Venus is almost not rotating. Okay, so you can see that they are almost perfectly spherical. Now, why planets are spherical is also because of the law of gravitation. The stars, planets, they are formed from clouds of dust which are attracted to each other due to law of gravitation. Okay, and they move faster and faster, and as they spin and move faster, they get attracted to each other, and eventually becomes a planet or a star. Okay, so that is how the type that's how they think it is formed in a way. Okay, so law of gravitation is like it pull inwards. You cannot have like one side more. We cannot be like square shape or triangle shaped planet. That's not possible. Okay, and that is why the bigger planets are all spherical. But however, you can see that the asteroid belt, there's a lot of rocks that are not spherical. In all sorts of shapes. And that's because the law of gravitation works more when there's more mass. Okay, when there's not enough mass, of course, the gravitational force is smaller. So a lot of other things will happen. Okay. So, and then as they rotate all these planets, you can see that the rotation period of Jupiter is very, very, very short. So it bulks a lot more. Okay. So these are all the different planets for you to see. Okay. So, yeah. Let's go through some Olympiad questions. Yeah, put it earlier. After capacitor. Yeah. Gravitation. There are only 4 questions. Of the 4 questions, you are only able to do question 2 and 3. Either 1 and 4 I will explain how to do. Okay, question 2 and 3. Question 3, you'll see this thing called EV, electron volt. By right, it's in quantum that they will test you, but I realized it was also in the 2018 paper. Yeah, so I will just tell you, it's called an electron volt. Is given as 1.6 times 10 power minus 19 joules. Okay, it comes from a charge of an electron. So you can use these values to try to solve question 2 and 3. They give you all about 5 minutes. Okay, so let's start with question 1. Okay, then I skip this. This is actually a 2018 paper. Just that the time it's in 2008 paper. Okay. Now, which of the following lists the 4 fundamental forces? Okay, so I didn't know where to classify. Which topic to classify this. That's why I put under gravitation because there's the word gravitation. Okay, so in physics, there are 4 fundamental forces. Okay, they just classify all forces under these 4. So there's gravitational force, weak force, electromagnetic force, strong force. Okay. In order of increasing strength, you can see the answer is actually just A. So gravitational force is the weakest. Weak force is like forces between molecules. I don't know how to explain it. Okay, you don't need to know it also. Electromagnetic force is just your electric forces and your magnetic forces. The interesting one is strong force. Okay, so strong force is the reason why, for let's say atoms, right, your nucleus. Okay, we all learn in chemistry your protons and neutrons, right? You know that protons are positive. So why wouldn't they repel each other, but stay in a small space in the nucleus? Okay, so what happens is that, okay, when you draw the atom, the Bohr model of the atom, right? Your nucleus, you draw very small, and the electron, you draw in a circle around it. Okay, wait, it didn't turn into a circle. But yeah, okay, let's do a circle. Something like that. Okay, you draw your electron with the nucleus here. Okay. Okay. So all your protons are inside here, and neutrons are inside. So you know that light charges repel. So why don't the protons repel each other? Okay, and the reason is because of this nuclear strong force. Okay, so the strong force will act inwards and hold the protons in their space here. Okay, that's just what strong force is. Okay, now if you were to actually look at the size, right, that's for your info, extra info. The size of the atom, that's how we mentioned, is about 10 power minus 10 meters. The size of the nucleus, okay, which okay, this is not to scale, it's 10 power minus 15 meters. It's like looking at a 100-meter track versus 1 mm on your ruler. That's the size difference. Okay. Okay. Question 2. So at the point out of Earth at a distance x from the center, Earth's gravitational field is about 5 newtons per kg. So, and the Earth's surface is 10 newtons per kg. What is the approximate value of the radius of Earth? So this is actually a two scenario question. Okay, so we know that gravitational field, you just need to know the formula. G m over x squared. In this case, it's 5. Equation 1. G m over radius of Earth square. This is 10. Okay. In fact, this question here, right? Sometimes a question may not give you the mass of Earth. So you can use Gm over radius of Earth square equals 9.8. So if they give you the radius but they don't give you the mass, you set this to 9.8, not 10. Okay? This, just like they give you is 10. Set this to 9.8, you can actually find the mass of Earth. Okay. Anyway, this is equation 2. So when it's scenario questions, I will just take equation 1 divided by equation 2. So get rid of the constants. So on the left side, you'll get radius of Earth squared over x squared. On the right side, you get half. So the radius of Earth is x over root 2. Okay. Question 3. Conservation of energy. Okay. Okay, let me use more space for question 3. Okay. So electron with this Ke moves vertically upwards from the surface of the sun. Okay. Wow. So calculate the height the electron reaches above the sun's surface. So it's similar to a question where you throw something from the surface of Earth and what's the maximum height. So there will be a loss in Ke equals gain in GPE. Loss in K will be 0.5 EV, so it'll be 0.8 times 10 power minus 19 joules. Gain in GPE, final minus initial. Okay, so final, okay, this they already tell you this is a GPE formula. Over R. Final minus initial. Initial is on the surface of the sun, so the R is RS here. Okay, we should know that you can just cancel. So all these are given to you. You know that this G is 9.8. Okay. Oh yeah, I forgot to give you one value. That's why y'all cannot do. You also need one more value. Mass of electron as 9.11 times 10 power minus 31 kg. I forgot to give you all this. Okay. So from here, you must find what is R. Okay. So what I will do is RS minus RS squared over R equals 0.8 times 10 power minus 19 over MGS. I put in terms of RS. Times divide by divide by 28.02 divide by 9.8. Four, five, 7, 8. So RS minus this. Two 696,000,000 minus this. Oh, so big. So divide by 696,000,000. Around I got 1.85 RS. Okay. So the question wants above sun's surface. This is distance from the center of sun. So that's why it will be 0.85. Okay. Question 4. Question 4 is another maneuver. It's called a gravitational slingshot. So basically what happens is that it borrows the momentum of Jupiter so that it can increase the speed of the spacecraft. Okay, so this has been used quite frequently by NASA to increase the speed, okay, without bringing more fuel. Okay, that's the advantage of it. Now, so what happens is that you need to use conservation of momentum, and it is assumed that such a collision, okay, it's like a collision, is going to be elastic. Okay, so let this be one, mass 1, this is the mass 2. Elastic collision, if you can remember, U1 minus U2 equals to V2 minus V1. Okay, elastic collision. Now, we U1 minus U2. Now, the thing about Jupiter is that its velocity at this point is going to be constant. Okay, it's just moving in this direction. It doesn't change. So, U1 minus U2, you can see that the difference here, the relative speed of approach is going to be 2v. Because U equals to V. Okay, this is U, this is V, this is equals to V. So the relative speed of approach is 2v. The relative speed of separation. So the spacecraft is now moving here. Okay, the spacecraft is moving here, but Jupiter is still moving here. U equals to V. Okay, so V2 minus V1. We need to take this itself is V2 minus V1 is here. So this is V2 minus V1, which is square root 2V. Is it? Hey, no, sorry. Careless. Again. The final velocity is unknown, not V. The final velocity is VF. Let's just call it VF. But Jupiter is still the same. So the change in V2 minus V1 is actually VF, and this is the V, negative V. This is the V1. So this is the relative speed of separation, which is the square root of VF squared plus V squared. Vector subtraction. Okay. So square root of VF squared plus V squared. So we solve for this. For V square equals to Vf square plus V square. Vf square equals to 3V square. So you get your final velocity as square root 3V. So in doing this maneuver, it went from V to square root 3V. There's an increase of 73%. Okay. The last one on gravitation, just now I mentioned I want to talk about the International Space Station. So why are the astronauts floating in the space station? Okay. So if you can recall from your circular motion, nice. So let's say again, this is Earth. The ISS is orbiting around Earth, okay, in a circular motion. So it's orbiting Earth in a circular motion here. So what happens is that, again, Earth's gravitational field or Earth's gravitational force provides the centripetal force. And in this case, it's provide exactly. So what happens, there will be no normal force, no contact force between the astronaut and the ISS. That's why they are floating around. There will be no normal force, no contact force between ISS and the astronauts because both are at free fall. They are free falling towards Earth, and at the same time, we are moving. So it's like they fall. So it becomes a circular motion. Okay, the gravitational force in this case is the centripetal force. Okay, indeed. So n equals to 0. No contact force. Remember, to be in contact, n must be greater or equals to 0. Okay, so this one is not in contact. Okay, can? Yeah. Okay, so now we'll go to the next part, electric field. Now, why I spend so much time on gravitational field is because electric field is just, okay, I wrote a lot of stuff. Okay, you can go back and read. But electric field, you can see that it's actually very similar to gravitational field. So you can go to the, okay, electric field starts from, there's 4 pages here. Okay, you can go straight to the 4th page and just see just the relationship between the two formulas. So this is for point masses or spherical masses. A law of gravitation is for point masses, just that we assume Earth to be a point mass at the center. And these formulas here is for point charges. The main difference between electric field and gravitational field is that electric forces can be both attractive or repulsive, but gravitational forces are only attractive. Okay, like charges repel, unlike charges attract. So at O levels, you already learn the direction of the forces, and these are the magnitude of it. Okay, so there's electric force, electric field strength, the more proper field strength for wording. Okay, electrical potential energy, electrical potential. Okay, it's the same as gravitational force, gravitational field strength, gravitational potential energy, gravitational potential. Exactly the same. This K here is a constant, same as G, and K is given by 1 over 4 pi epsilon naught. Epsilon naught is a constant that's called permittivity of free space. So it will be given to you as 8.85 times 10 to the power of minus 12. Okay. Now, the only thing for electric field is that there's also parallel plates electric field, not just point charges. So for parallel plates, the formula is slightly different. For parallel plates, okay, page 2, this is the electric field for parallel plates. V over D. V is the potential difference, D is the perpendicular distance between them. Okay? And the last formula is just this one, work done. Okay, W equals to QV. This is from your O levels actually. Okay, so if you can recall, what is the definition of potential difference? Is the work done for you is work done to drive a unit charge across 2 points through a circuit component. Okay, so to be more proper, it's not just the work done to drive a unit charge, but it's the work done per unit charge. So your potential difference is the work done per unit charge. Okay, I think I talked about this the last lesson under dimensional analysis. Okay, so these are the few formulas you need. Now for these parallel plates, okay, it's a self-study thing. So it will be on this page 5 here. Everything is written inside the whole the work example plus the work solutions. Go back and read. Okay, basically, first half is on electric field. Second half is on your kinematics, projectile motion, SUVEC methodology. So you mix these two together. Okay, this is for you to go back and read. Okay, so we'll come to this question. Electric field, the basics. You have only 2 questions. We'll go through 2 questions. Neutral point, I will let you all go back and do. Okay, you can do this first and second question. Then after that, we can go on to capacitance, which is also quite simple. At least the part that is tested is simple. Okay, 5 minutes for the question. I'll write in the electric force formula for you. A Q1 Q2 over R square, where K is 1 over 4 pi epsilon naught, and epsilon naught is 8.85 times 10 power minus 12. So all these will be given in the list of constants here. Okay. So this one is actually quite simple. It's based on your lesson 1. Okay, so what I want to show you is that when you learn the formula for force, it's just for you to determine the magnitude, and with like charges repel, unlike charges attract, it's for you to determine the direction. After that, it boils down to resolution of forces. Okay, so there are 3 forces. There are going to be 3 forces here. The tension, we let this angle be theta. The electric force of attraction, and the weight. You only need to consider the force on the 5 nanocoulomb. Okay. Nano is 10 power watt, can you remember? Minus 9. So for prefixes, right? Okay, you all learn milli, micro, nano. There's still pico and femto. Okay, PICO is PICO, is FEMTO. This 10 power minus 15. So on the bigger side, 10 power 3, 6, 9, 12, 15, that's kilo. Okay, I use computer to remember kilobyte, megabyte, gigabyte, terabyte, petabyte. Okay, tera TERA, peta is PETA. Okay, you know. Okay. So now for this case, because these are the forces, we know it's an equilibrium. Okay, just consider free body diagram on a 5 nanocoulomb charge. So T cosine theta is equals to mg. T sine theta equals to the electric force. So you can calculate the electric force as 1 over 4 pi epsilon naught. Q1, 5 nano. Q2, 3 nano. Don't need to use the negative sign. For forces and fields, okay, we draw in the direction. that is what the negative sign is for. It just tells you that it's an attractive force. So forces and fields we don't add in. Only for energy, then you need to consider it. So over 5 mm square. .85. Okay, then times 15 minus 18 divided by 5 negative 3 square. You should get 0.005395 newtons. And the weight is 2 grams. Okay, so this equation 2, this equation 1, if you take 2 divided by 1, you get tangent theta. Okay, which is the electric force over the weight. So from here, you can get theta equals 15.4. Okay, the maths I leave it to you all to do. Okay. Okay, conservation of energy. This is pretty straightforward. Okay, the answer to this is also at the back. Okay, but last the final page, you can see that the final page there's also conservation of energy and conservation of momentum. Okay, here I only put one, but behind there's two. And at the last page there's two. So you can go back. I will leave it to you all to go back and read through. This one is quite similar to the gravitation one. Okay, so there's a one with similar to gravitation. There's one that requires conservation of momentum. Okay, actually both requires conservation of momentum because I just want to talk about this closest distance of approach. So closest, when will they be the closest together? Okay, they are nearest to each other when they have the same velocity. Okay, if the velocity is different, they will either be going further away or coming towards nearer to each other. So it can only happen when they are of the same velocity. So you can see that for this case, the initial momentum is going to be 0. So when they are at their closest distance, because the initial momentum is 0, they are closest when they are on the same velocity. That will be when v equals to 0. Okay. The final page, you can see the question, right? There will be one more where one proton is moving and one is stationary. So the closest is when they are moving at the same velocity, 5 meters per second. Okay. So this one, I'll leave it to you all to go home and study conservation of energy. Exactly the same. Okay, they are not hard. All the things are written there. Okay. Okay. So that is for up to electric field. Okay. One more thing, neutral point. Okay. This one, okay, I should have put a values in, but never mind. I'll just tell you what the idea. By the way, I came out with this like 10 years ago. Then this one came out at A level 3 years ago. Altered it before that. But 7 years early. Okay. So come back to this. How do you draw your field? O levels. When you have a plus and a plus. Versus, in this case, a minus and a plus. Okay, let's say these are the two charges are the same. When they are the same charge, let's say they have the same magnitude, you know that the neutral point is at the center. Okay, now you know neutral point. Okay, that's why they put X there. Now, normally I tell students to do this. This for O levels, okay? I will put a vertical line here that is very light, or just use a ruler. and you draw as though you are drawing an asymptote. Okay, so you'll do like, this is how your few lines are like. Okay, and then you continue drawing. Okay, I'll leave it to you all to draw the other side. Okay, so you know it's going to be like this. Just that this is extra info for you. When you all draw these lines, remember to cut here at 90 degrees. Why cut here at 90 degrees? Now you learn the law of gravitation, you learn the electric field. Electric field is called Coulomb's law. That's why I didn't give you a name. Look, Coulomb's law. Okay. So it is always directed towards the center of the charge. And because that's why you must have to be 90 degrees, so that all the lines will intersect at the center. Okay. Now, for this, how do you draw? Okay, let me just draw again here. Okay. So for this case, we draw a few lines. And you know that they are going to be like from year to year. And then this one is this one's going to be like that. Okay. Never mind. Okay, and you know it's going to be like this. Doesn't matter how it's drawn, So what happens is that you can see that the neutral point is not at the center anymore. At the center, there will always be an electric field. So in this case, anywhere in the center, because this is negative here, there will be an electric field due to the 3 nanocoulombs towards the left. There will be an electric field to the 5 nano also towards the left. So the neutral point will never be here. The neutral point is actually somewhere here. Okay, why? Because in this case, due to the 5 nano, it's going to be here. Due to the 3 nano, it will be in the opposite direction. Okay, so neutral point, the net electric field must be 0. So you solve, okay, by letting this distance be r. Okay, so for this case, because the electric field is 0, K, Q, again, we are dealing with field, so we can ignore the negative sign, over 10 power minus 3 plus r square equals to K 3 nano over r square. Okay, and just remove the K, remove the nano. 5r square equals to 3 10 power minus 3 plus r square. Square root both sides. Or the negative version, okay, we should reject. So you can get your r. I think it's 3.44, if I remember. Root 3 over root 5 minus root 3. Yep, 3.44 mm. Okay. So that is neutral point when they are minus and plus. Now, if they are both of the same magnitude, there will be no neutral point. It will never be possible to find a place where this one is smaller and they are equal in, how to say, you will never be able to find a place where they are equal. The E fields are equal in magnitude, opposite in direction. Okay, so neutral point can only be found if they are of opposite, if the charges are not of the same magnitude. Okay, that's more mathematics. Okay, so few questions behind are all quite similar to what I gave you. Okay, so I think that is, if I remember, there may be one or two that's not solvable. It's okay. No, that's the circuits one. That's the part of the circuits one. Circuits one, I think the teacher will give you all next week. There's one circuits one that's not solvable because you require something called Kirchhoff's law, which is not inside already. So there will be two more documents that you all will get. So one is I think it's the next lesson. One is on optics, one is on circuits. So each of them have one hard question, which I will upload the video solution onto the playlist. Okay. Then there will be one question in circuits that is not doable. You'll see that there are two EMF sources, so that one will not be doable. Okay, at least for you. Okay, last thing to go through, capacitor. Okay, there's some extra stuff that we don't need here. Later part, okay? So I'll just go through quickly. Now this part, right, for this, the equations for this capacitors, right, I forgot to put inside the formula list. So my next edition, I'll probably remove the left and right hand rule and put it inside. Okay, that will be this formula and this formula. So you may want to write it inside. Okay. So capacitors, okay, this is a circuit device. It's like your resistor. Okay, you have learned in your circuit there's resistor, there's light bulb, there's this and that. There's this thing called capacitors. There's one more thing called inductors. By right, you need to know both, but we don't have time to go through inductors. Okay, so you might want to also read through, apart from those I mentioned at the start of the lesson, you might want to read through inductors. Okay. Now, capacitors, right, is just a device to store charge. Okay. Your power banks, all these, if you have, okay, are all in a way capacitors. They store charges. Okay. So capacitors, right, the simplest design is two metal plates that are parallel, separated by an insulator. So this insulator, it can be air, can be anything. We call it the dielectric. The name is here, dielectric. Okay. So capacitance is defined by this formula, C equals to Q over V. Okay, the SI unit is the farad. Yeah. Okay. I find this easier to remember. Q equals to CV. Somehow I find this easier, but yeah. C equals to Q over V. Okay. And the capacitance, right, of a parallel plate capacitor is usually given by this. For air, we will just use this because this is 1 for air. Okay. Sometimes they give you the value like this. Okay, just give you a value for this. Okay, if not, usually it's for air, it's going to be this. This is the permittivity of free air, 8.85 times 10 power minus 12. Okay, we did that, use that for electric field. So you can see that the capacitance, right, is larger when you have a larger area or a smaller distance between them. Okay, so for at least for the secondary school Olympiad, this I think your capacitance will be simple. It will just be this. So if you are taking a JC Olympiad, your capacitance can also be. They can also use, I don't know, sphere. They can make it turn in a circle, and then you need to use integration to solve. Yeah. That one will be very tough. I also don't know how to do. Okay, so capacitors, because it's circuit component, okay, it is similar to the resistor in a way. Okay, so capacitors, when it's parallel, right, you can see that the equivalent capacitors, the equivalent resistance like that. Okay, effective capacitance, effective resistance. But capacitance is just opposite of resistance in the formulas. So when they are parallel, just sum them up. When they are in series, reciprocal. Okay, very straightforward. And because they can store charges, it also means that they can store energy. Okay, so the energy stored half Q square over C or half CV square is still good enough. Okay, it's like your power bank. You store when you charge it, you store it's actually storing energy. So this is the energy that is being stored. Now, how do you charge a capacitor? Now, all this below, right? I look through the syllabus. I think the likelihood, I don't think it's in just put here only. Okay, so this part, the formulas, I don't think is in. It's just for you to understand how a capacitor is being charged. Okay, so a capacitor is charged, right? Okay, let's say, okay, we talk about EMF source first. So a battery, a EMF source, actually sets up an electric field to force electrons to move in this direction. Okay, that's why we call it electromotive force. You give a force, you set up an electric field to give a force for the electrons to move here. And when you move through the resistor, the resistor resists that flow. Okay, that's called a resistor. So you need work to move through the resistor. Now, because we move these electrons in this direction, right? This capacitor is initially uncharged. And when you move negative charges, which is electrons, from this plate to the other plate, this eventually becomes positively charged. This will become negatively charged. So what will happen? Here we call it plus Q. Here we call it minus Q. So it's charged with a charge of Q. Okay? No current actually moves between there. Here, no current. It's just the charges from this plate move to the other plate. Now, without this resistor, right, this movement is instantaneous. Because no resistance. Remember, the initial current, right, is still E over R, V equals IR. Okay, the initial current is still this. So if there's no resistance, current, which is the flow of charges, the rate of flow of charge, is infinite. So imagine if the flow is infinite, it will flow very fast until this capacitor is also 24 volts. Oh, sorry, it's also E. Okay, so because of that, right, this and this counter each other, no more current flow. Resistor slows down the rate of flow of charges. Higher resistance, smaller current. So if the rate of flow of charge is slower, it takes time to charge. That's why you get all this here. Okay, calculations wise, I never see it before, so I don't think it will come up. Just know that it takes time to charge when there's a resistor. Okay, and it takes time to discharge when there is a when there's a resistor. This discharging capacitor. They cancel out because when this plus Q and negative Q, right, there is also a voltage because Q equals to CV. So it becomes such that your capacitor looks like this and then like this. So in a way, they cancel each other. So it's like, yeah, you can, even if you have a resistor R, there'll be no more current flow if they are the same. Because we charge the capacitor until it becomes this. If not, the current will keep flowing and keep charging it. Okay. Now, quick questions. Okay, this one I let y'all go back and do it. It's pretty straightforward. I'll just tell you what you need to do. All these questions came from the university textbook. Okay, it's strict. I chose the straightforward ones. This one is as though there are two capacitors in parallel. Okay, number one, number two. So we'll be using C equals to dielectric constant epsilon naught A over D. So for K1, K2, parallel, sum them up. Second one is just that they are in series. Nothing special. Okay, just to show you parallel series, and this one I think should be obvious enough. This is the K1 in parallel with this and this. So for this, you do, let's say this C2, this C3, this C1. this will be 1 over C2 plus 1 over C3 inverse. That's this sum up with C1 will be the effective capacitance. Okay. Can I? Now I only want to go. This one is still an easy one. The tougher one, I think I will write something for you. I don't have a tougher one here yet. I'll write something up. Okay, so what happens here first is that you can see that C1, C2 are in series together with the effective of this. Okay, so this is 30 microfarad. This is 30 microfarad. Okay, this one is actually coulombs. So this is microcoulomb. So these two, because it's 15 and 15 in parallel, it is also 30 microfarad. So it's something like resistance. Okay, V1 plus V1 which is across this, plus V2 which is across this, plus let's call it V3 which is across these two, must be equals to V. The sum of the potential difference must be equal to this V, right? And this tells you that Q1 over C1 plus Q2 over C2 plus Q3 over C3 is also equals to V. Now for this question, C1, C2, C3 are the same value. I don't mean C3, I mean C3 parallel C4 in this case. Okay, so these three are the same value. That's why the Q are all of the same value. Okay, now we consider again why okay, let me explain a bit more why the Q have the same value. Let's say you have these three capacitors here. The key is they are initially uncharged. Okay, so we know that the charge moves from one plate to the other plate. So if this is plus Q, the charge will move to here negative Q. Here is plus Q, here must be minus Q. These two are the same. Here will be plus Q because the charge moves from here to here. The electrons move from this plate to this plate. Okay, same thing here. If they were initially uncharged, the total charge here should still be 0. This is called conservation of charge. Okay, so this is when they are in series. Okay, there will be one more type of question, which I don't have time to go through. I'll just show you all straight. Let me see if I have it here. If I don't have it, I'll write an example for you. This side, question 3. So this switch first charge this C1. Then after that, it's connected to here, and C1 will now charge this 3. What are the final charges? Something like that. Okay. This one probably you can't see. I will write down one for you with values. Okay, and one example. Then after that you'll see it. Okay, this one yeah, I'll try to do it. So both coefficient of restitution and this one. So you'll have 2 more things to read. Yeah. Okay, I don't think I want to keep you back. Okay, so for this remaining thing I need to do is just to read the parallel plates electric field with projectile motion. Okay, then after that I'll try to do 2 more documents for you all to self-read. And the last thing is the last 2 questions here. Okay. Okay, so that will be for today.